Sequences in series, there's really only, what is it, 11, 1, 11, 2. So that's all there is to it.
And that's all you have left?
Yes, and then we're going to sit around and do Jack Diddley Bumpkus for the rest of the show. Yeah.
But not gambling, because gambling is wrong.
So there's only 4 sections in this, but there's going to be a handful of formulas. I will give you the formulas. I won't tell you which one is which. Okay? Because you'll have formulas for what are arithmetic sequences, arithmetic series, geometric series, geometric sequences, and then you'll have infinite series as well. You'll have to know what to use and when, and how the things work. So don't worry about memorizing any of these formulas. You'll always get them. I also put those on the final, so it's one of those things you don't have to worry about. What else was there on this? Yeah. So sequences and series. One of those would be technically what do you call it? A sequence versus well, one of them. I'm sorry, rephrase this. One of them is finite, and one of them is infinite. Which is which? Why is the other one infinite? The dot dot dots. Those would actually be. What is it called? Really? Is that what it's called?
Yeah.
I didn't know that.
Yeah.
Oh, cool. Thanks. So this is called this one is a finite sequence, and this one would be infinite. What happens here is that you get domains and ranges. Okay. The values that you're seeing are the values within the range. The domain becomes the number in the sequence itself. Okay. So if you think of it this way, if this is our domain, my domain, and this is my range. This is the first term of the sequence, second, third, fourth, fifth, and so on and so on. That's what that stuff means. You've got first term sequence, second term sequence, so on and so on. What this allows us to be able to do, or if you want to think of it, we're going to use what are called subscripts. You guys have ever seen subscripts before? Huh? It's the number below. It's yes. Yeah. Yep. It's supposed to be sub 1. You're right. Look at you, the memory on you, the bad Murphy stories. Atta girl. So what I would say here is that my first term is 3, my third term is 9, my fifth term is 15. That's how that would look. Okay, that's what that means. Okay. A is a number in this. Bless you. Okay. They use the terminology A sub n, where this is the nth term. You'll see that a lot. Start with this stuff. It's some basic vocabulary and some background stuff. What we'll be able to do then is we'll be able to take these values within sequences and stuff, and we'll be able to figure out specific terms. A lot of times when you're looking at this first term, or what are the first terms within a sequence, there's a couple ways of doing this. If you're looking at the first 6 terms of a sequence in the first one, you've got a sub n is 2n plus 3. That means you're putting 1 in for n 6 times. 1, 2, 3, 4, 5, and 6. Why? Would you like me to make this? I mean, I know this is a lot for a Wednesday. What's that?
So like 1 through 6 of the sequence of the sequence.
This is the rule, what we're going to call the general rule of a sequence.
Okay.
All right?
So you mean just like the number value?
The reason why I wanted to show you guys this part is because over the past couple of years, I've kind of skipped over writing out the sequence. And I've realized that by skipping over writing the sequence, you kind of lose the idea of what number sense looks like. So by doing this, you're going to create basically the finite sequence for 6 terms. Okay? You're creating the sequence given a specific equation. It's going to allow you to understand how numbers and number patterns work. So that way when you look at a sequence, you'll be able to write the equation. You'll be able to work backwards. So this is real tough. I know, I'm hoping that we'll be able to do this. 2 times 1. Darn it, we were so close. 21, right? Yeah. So this becomes 5. Now what? So the sequence that equation generated was 5, 7, 9, 11, 13, 15. Okay. So the first term is 5, second term is 7, third term generates a 9, and so on and so on. Same thing happens when you look at -2 to the n minus 1. Same idea. When we start putting them through, you've got your first term. Be -2 to the 1 minus 1. -2 to the 2 minus 1. Okay. Whew. Order of operations tells you to do what first? All right. 1 minus 1. What is anything to the 0 power? Okay. So the first term in the sequence would be 1. The second term in the sequence would be -2. The third term in the sequence would be 4. The fourth term in the sequence would be, very good, 16. You don't need a calculator, you're just multiplying it again by 2. And this would be -32. Now, I wanted to make sure I showed you guys this one with, notice how the values within the sequence are alternating signs. This is one way that, a way to change signs within a sequence is to raise an exponent. And that'll come up when we start to try to figure out working backwards. It's one of those tricks if you're trying to figure out an equation to something, you might mess around with the exponents and their signs. And when I mean signs, and not S-I-N-E, it's S-I-G-N now. It's a tough crowd. It's not even that, it's just making me sad. I don't need to do those. Let's write some rules. So, if I want to write some rules, oh, there they are. I made notes. So I didn't screw something up. I want to write a rule for -1/3, 1/9, -1/27, and 1/81st. And I want to write the rule for that sequence. When I talk about write the rule, I'm going to write in terms of n. One of the easy ways to do that is to write it out as your first term is -1/3. Your second term is 1/9. Your third term is -1/27. Your fourth term is 1/81st. Now, when I look at it like that, I'm trying to figure out, and it's kind of nice that I just mentioned about, notice how these signs have alternated, which meant that somehow you had to mess around with your exponents. Also, even though it's fractional, how do you go from 3 to a 9 to a 27 to an 81? What are they doing to it? They're raising it to an exponent, aren't they? Okay. So what we want to try and do here is try to figure out what would the equation be to generate these values. Now, what's nice is that you can start writing stuff out and kind of guess and check, which isn't a bad idea. But you've got this great, powerful thing that's not your cell phone. You've got this great yellow thing that's not your cell phone. That you have this button on there that says y equals. I don't know if you've ever seen that before. And then there's a button on the top right corner that says table. Have you seen that? So what's nice is that if you start guessing around with different formulas. Remember we did that the other day? Dampen sign functions? So what I did here is I dampened the sign functions with, I did cosines and sines, positive and negative absolute values, and just it looked really cool. I could shade all of it too. Why not?
How would you shade it?
Press a button. You have to know which direction you're shading to do it. So I did above. So I got it. So I can shade and do all this weird. I could probably be able just to shade in the interim if I really wanted to, but I don't remember how to do all that. So I'm not gonna do it now. So sayonara sign functions. Fix this. All right. Okay. So what we're doing here is we take a rough guess of what you think it might be. Now, if your first term is, what was it, -1/3. So if our first term is -1/3, what we start thinking about is, what would I have to raise that to for an exponent to try to make the first term negative? Or what would you do for the first term if you have to make the term itself negative? What's the difference between doing this versus this is a nice little trick to, yeah. What would your first term be if it was n-1? It would be 1, wouldn't it? Okay. The first one would be 1. Now, if I do the first term on the other one, if I do a -1/3 to the n, if n is 1, what's my first term? negative 1/3. If n is 2, it'd be I squared, it becomes 1/9. That's the idea when you start messing around with some of these things. You start playing with the exponents. And it takes a little bit of time just to get to a lot of trial and error with some of this, because some of them can get kind of weird. Okay? Now, if you put that in the calculator, you'll see if you use the fraction bar, parentheses alpha y equals, you guys remember how to make fraction bars, right? So negative 1/3, so I put it over 3 to the x, and then go to your table, and then you can verify to see if you were close. And obviously, as you go through, and there it goes. Okay. It's trial and error. You get a lot of trial and error this way. Okay. There's going to be a lot of error to begin with. That's usually happens. That's usually what happens. Thank you, sir. So let's look at the other one.
We have to describe the pattern for the next term.
What I'm going to do is ask you to write the rule for the other term. So if I look at one like this, think of it in terms of the same way. Your first term is 2. Your second term is 6. Your third term is 12. Your fourth term is 20. Now, if you look at what's happening here, what's happening between the numbers? It's going up. Yes, very good. You were able to describe that it's increasing. So the next one would probably be what? Probably 30, wouldn't it? Okay. So what we have to do is figure out how are you generating the next number. Now you're adding, okay, but it's not a constant value that you're adding every time. Okay. So what happens here is that when they're not what we call arithmetic, an arithmetic sequence is a sequence that has a common difference. And we'll do that stuff on Friday. When you talk about this case, you're looking for what would be, I mean, you described the pattern, right? You went up by, what, 4, 6, 8, 10, the next one would be 12, and so on and so on. But how do you go from the first term, somehow the first term generates a 2, the second term generates a 6, the third term generates a 12, the fourth term generates a 20. How are you going between each of those? What do you got, John? No, say it. I think you have it. Okay, what do you have?
You take 2 times.
2 times n, then add 2. So you're saying 2n plus 2? All right, if it's 2n plus 2, if my first term is 1, what's 2 times 1? Remember with that? And that's the idea. You start messing around with it. What do you think, Sword?
You do n times 2, and then you.
So you're saying n times n plus 2? Okay. If you go that route, if your first term is 1, what's 1 times 1 plus 2? 3. Okay. You're getting close to it. It does not. Exponents usually involve when you're changing signs. Or you'll start to see that the numbers themselves are being squared, cubed, and so on. Go with your pattern you just had a second ago. Sorry. your n times n plus 2. Yeah. If it was 2 times n plus 2, again, if n is 1, what's 2 times 1? 2, and then you'd have 2 plus 1, which would be 3. So your first term would have been 6. Okay. You're starting at your first term is 1. Two parentheses n plus 2? So you're saying, what if it was 2 parentheses n plus? Okay, again, if the first term is 1, if your first term, your n is 1 for your first term, what's 1 plus 2? 3 times 2 is, and that's not my first term. There it is. Sawyer, you were really close. Okay. The idea here is this takes a little bit of time to go back to number sense. It's been a while to try to figure it out. It's going to be a lot of trial and error. As you go through n times n plus 1, well, if the first term, if I'm using n for my first term, when you put that in your calculator, you can kind of, it's the easiest way to double check these things. X plus 1. This is the easiest way to double check yourself. First term is 1, generates a 2. 2 generates a 6. 3 generates a 12. 4 generates a 20. 5 generates the 30. 6 generates the 42. 1 times 2, 2 times 3, 3 times 4, 4 times 5, and so on and so on and so on. If you think of it that way, it was the next two numbers consecutive multiplied together. 1 times 2, 2 times 3, 3 times 4, 4 times 5, and so on and so on. How do you just write that out in terms of n? And that's what takes time to get used to. Right? Okay. Series. Difference between a series and a sequence is that a series, you're adding them each consecutive term together. So a finite sequence is just your, thank you. It's just your regular boring 3, 6, 9, 12, or and so on. When you get to the series, you start talking about what's called the summation of something. Summation has its own notation. It's called sigma notation. Okay? Finite series versus an infinite series. One way to write, instead of writing this out in terms of all these pluses, what we use, is this thing called sigma notation. You may or may not have seen this before. You ever seen that before? Yeah. Nope, not ever. Now, it is the Greek letter. It's the Greek letter sigma, and you're right. Sigma is a sorority. It's like delta, delta, delta. Can I help you? Help you? Help you? For some reason, I think you're mocking me. Shut up. So, what happens here with this thing called sigma notation? This is the Greek letter sigma. It stands for sum. Okay? It stands for adding things up. What happens is you start with where you start with the first term. It goes through 1 little, 2 little, 3 little terms, 4 little, 5. There are 5 terms in the sequence. How many times you're adding them together? And then out front here, you write the rule. Now, the rule for 3, 6, 9, 12, 15 is what? What would that be in terms of n? How do you generate that sequence? It's 3n, isn't it? 3 times 1, 3 times 2, 3 times 3, and so on. So out front here, this I would put, it's actually a really good circle. That's all that means. Okay, that's all that means. That means take 3n, which is the sequence, and find the sum of the 5 terms starting with 1. You can start at 0, you can start at -6. It just means what number you start with and how many of them you put in the sequence to go through. Okay. The difference between this and an infinite series looks exactly the same. And at 1, the rule, but up top, instead of writing a 5, we put infinity. The hyperbolic paraboloid.
Infinity.
It's a Pringle. I told you guys that, right? Really? I didn't tell you the Pringle story? All right. The guy that invented the Pringles was a math person. He didn't like broken chips, and I know you can still get chips broken with Pringles and all that, but not as many. If you think about in nature, what's the strongest structure in nature? Arcs. Like triangles, elephants, whatever. No, it's arcs. So in a Pringle is just a giant curve. Well, in mathematics they are. So what happened was he was trying to figure out a way that you can stack them that creates strength. So he developed the idea of using what's called a hyperbolic paraboloid. This is not a 20% BS story. This is an 80% story. The hyperbolic paraboloid, which would stack upon itself, was stronger than the other ones. That's where it came from. That's why Pringles look like that.
You said this is not a 20%. This is 80%. So what I'm getting from this is that's 80% BS.
No.
That's basically what
Well, it's not what I meant. You'll miss my funny stories. No, you won't. Hey, guess what? There's no infinity button on your calculator, just so you know. There is no infinity button on your calculator, but there is a sigma button. Alpha, window, zoom, trace. Forgot where it is. Wasn't it zoom?
Alpha window zoom graph table. Let me go ahead and change up alpha window zoom graph to a potato squash versus zucchini.
Where is my, number 2, right there. Summation. Alpha window 2. So what's nice is that you can do summations in the calculator itself. I would not, because the summations that you're doing are so quick. It's a lot easier to do it by hand versus the amount of time it takes you to put them all together. First thing you put an x equals 1, and move it over to the next part. You have 5 of them, and you go 3x, and then you hit enter, and it does the work for you. So the reason why I wanted to show you that, I don't know if there was any summation stuff. Was there any summation stuff on the SAT at all?
Oh yeah, all of it, dude.
I think there is there on the ACT? So at least now you know what button it is. You still got time. Okay. 3 plus 6 plus 3 plus 6 plus 9 plus 12 plus 15. Real quick, stop. Don't write this. I know this textbook, this is the old textbook, and this is the one thing I didn't like from them. They do use I. It's not imaginary, okay? It's not an imaginary. This is just a variable. I know it's definitely scarred you through this. It's okay. It's just playing the role of variable, okay? Let's write this in summation notation. This is a finite sequence. So what happens with this is that you just have to figure out the generic rule first. Figure out the generic rule, and then figure out how many of them there are. it'd be this for N if you're trying to use sign language. I would go sign. No, sign is this. Actually, I think it would be this. No, I'm not. No, I'm not trying to. No. I'm really not. I'm sorry. I feel awful now that I did. No. This. I know this is N in sign language. I know this. I'm not trying to make fun of anybody. I mean, I do try to make fun of people, but not like that. I was making a joke about the like sign. I'm like, oh, this is sign. And they're like, no, would it be with your fingers? Thanks for making me feel like really bad. Do you know sign language?
We learned the alphabet
Oh.
in kindergarten.
A, B, C, D,
I speak English.
J, M, N, O.
Z was like you literally draw. Z was like you literally draw Z.
That was Z. Anyway, so what's the sequence? What's the rule here first? 5x. Does N start? Guys, does N start at 1 or 0? How many of them are there in said sequence? What's really funny is that this textbook wanted to show you guys that there are some really, really weird formulas of how to convert something squared for 12 times that you'd have to do this out by hand. Well, that's just silly because guess what? You have calculators with buttons anymore. So this is really gone by the wayside. You do not need to, I don't know what to do here. I gotta do it. Can you imagine having to do that by hand? No, that's not fun. But there's a button. Merry Christmas. Well, do these, but there's one of them I want you to skip over. Skip 23, and I think I might not start you at 9. I might start you a little bit earlier. Yes, sir. Start at Start at 17. Okay? All of this is it's 17, 19, 21, so on and so on. Will you double check for me? I believe I put the PDF file online yesterday. Today, and I'd rather you not use that snotty attitude with me. I've had about up to here with you, Mr. Carter. Does it get worse? That's true. What do you mean? Oh, I've had it up to here?
I don't care.
Yeah, just wait till your father gets home. Wait till your mother gets home. Have you done your homework?
You're not old enough to
This is a mom and dad joke. You're not good yet. We get that a lot too. I want to see that. No.